All right, welcome to the 3.7 notes on the chain rule. So as we start, we just want to take a look at some compositions of functions and see if we can find a relationship between their derivatives of each individual function and the derivative of the composition. So let's say that we are given that f of x is equal to x squared and g of x is equal to 3x. Why don't you pause the video really quickly, find the composition, find the derivative of each expression individually, and then see what you think the derivative of g of f of g of x would be. And when you're ready, go ahead and restart the video. All right, so the derivative, if f is x squared, then f prime would be 2x using the power rule. For g of x, its derivative would be 3. Now the composition f of g of x would be something squared, and then the input would be 3x plus 7. We're going to FOIL and expand that out, and we'll end up with 9x squared plus, let's see, that'd be 42x plus 49. So now that I know what the composition is, I could go ahead and take the derivative of this composition by using the power rule, and I'd end up with 18x plus 42. And I'd like you to compare that to the individual derivatives here. This is not a derivative of each derivative individually and then making a composition. I couldn't just take this 3 and plug it into 2x. I would just get a derivative of 6, which is not the same thing. So we need to have a different rule in order to do this. Now, I will give you bonus points. I'm sure Mr. Gannon will too, if you can actually derive the rule or find it online and then try to put it into terms that is understandable for a high school student. But here's what the chain rule says. If you are trying to take the derivative with respect to x of the function f of g of x, what you would want to do is you want to start by taking the derivative of the composition of, so the derivative of f that's been evaluated at g, but then you need to multiply that by the derivative of g. So I actually think this one will work really well when we can see it by using a chart or a table, and then we'll work with some expressions. So we want to find the derivative of f of g of negative 2. So again, I'm just going to kind of reference that formula up here. So the derivative of this would be f prime evaluated at this inner function, which in this case is g of negative 2, and then times g prime evaluated at negative 2. And we're going to use the table to find these things. We are going to still evaluate these from the inside out, the way that you learned in previous math classes. So we'll start right here with figuring out what g of negative 2 is. So g of negative 2 is 3. So this would be f prime of 3. And then I want to multiply that by g prime at negative 2. So f prime of 3, I want to make sure I'm using this column now for f prime. F prime of 3 is negative 2. And then g prime, so now I'm using this column, evaluated at negative 2 is negative 7. And when we multiply those together, we'll get 14. So this chain rule part here, I just kind of want to make sure and mention here. So we're basically, what we're doing is we're taking the derivative of the outer function and we're taking that being evaluated at the inner function, and then we are multiplying that outer function's derivative times the derivative of the inner function. So one of our challenges is going to be to figure out what is the outer function, what is the inner function, and then we'll practice using the chain rule. So here's an example here. And so these are already written as compositions. And so we really do have to stop and figure out what is the outer function and what is the inner function. So in this particular situation, the outer function is something cubed. And so what we want to do is we want to take the outer function first, and do the derivative rule that would be appropriate for that form. So if I'm trying to take the derivative of something cubed, I would use the power rule. So I would take that power of 3, and that would be multiplied the coefficient up front, which is an unwritten 1, and then reduce that power down to a 2. Now, what our chain rule said is that this needs to be evaluated at the inner function. So I'm going to keep this inner function as still the base. And then I need to multiply this expression by the inner function. And this inner function being a binomial, and I'm multiplying by more than one term, I do need to put parentheses here. And so this would be 3 minus 4x. Now I'm actually happy with this answer because everything is already factored. And I guess I could take an x out here. This is probably pretty common as how it might be written, but you could take an x out of each of these factors squared if you wanted and have a 3x squared out front. But I think I'd accept this answer. All right, let's take a look at number 4. So again, our challenge is to figure out what is the outer function and what is the inner function, and that's going to be important as we work on doing the chain rule. I'm going to actually rewrite this by using a rational exponent because it is going to be helpful in terms of identifying what's happening here. And so I'm both squaring and cube rooting, and so my power here is 2/3. So the outer function is really something to the power of 2/3. And so when I do my derivative, I want to start by following the derivative rule for this type of form, which would be a power rule. So I will go ahead and multiply by that coefficient of 2/3 and then reduce that power by 1. And now what I want to do is I want to make sure that I keep the original inner function still needs to be the inner function as I've taken this derivative pattern. And then I want to multiply this by the derivative of the inner function, which will end up only being one term, so there's no need for parentheses. This one, although it is already factored pretty well, I could still do a little bit of work on this one. So I'm going to go ahead and start by taking this negative power and moving it to the denominator. It's a cube root. That could be factored, which I'm going to do in just a minute. On the denominator, I would have a 4x, and on the numerator, pardon me, I have that 4x, and on the denominator, I have a 3. And I am going to factor inside my cube root. You might wonder, why do we factor these? There's actually a useful purpose. When we get to the next chapter and we see how derivatives are going to be used for graph analysis, it's actually really useful for things to be factored. All right, number 5. Why don't you pause the video and try number 5? As a hint, think about rewriting this with a negative power to start off with. This is not something you should be using the quotient rule for. Although the quotient rule is possible, it's way harder than it needs to be. All right, so I'm going to go ahead and show you the solution for this. I'm going to rewrite g as -7 times 2t minus 3 to the power of -2. And so really what the outer function here is I have -7 times some base to the power of -2. And so when I do the derivative, I'm going to start with the power rule, and I'll get positive 14 times whatever that base is to the power of -3, because I'm taking 1 away from the power. Whatever that original base was needs to still be written here as the base of this derivative. So this would still be 2t minus 3. And then I do want to multiply this by the chain rule. So the chain rule is what tells me I need to multiply by the derivative of the inner function, which is 2. And so if I rewrite this, the 14 and the 2 would be a 28, and I do have a negative power. So I'm going to move this quantity to t minus 3 quantity cubed out of the denominator. For number 6, we want to find the second derivative of this function. And again, this is not a situation where you should be really using the chain rule. Using the quotient rule. Although it's possible, it's by far more labor intensive and much more likely that you're going to make errors. I would rewrite this function as 1 times, I guess that one's not needed, -3x plus 2 to the power of -1. If you wanted, you could rewrite that as 2 minus 3x, which I kind of prefer, but I'll leave that up to you. All right, so if I do the derivative, I want to make sure I can see what the outer form is, which is a power to the negative 1. So I'm going to use the power rule. And that would leave me with a power of negative 2 when I subtract 1 from the power. I do want to keep the original base of negative 3x plus 2. I don't know. I'm going to write this 2 minus 3x. I just prefer not to lead with a negative. That's just personal choice. It's up to you. Now, before I decide that I'm done with this first derivative, make sure you multiply this by the inner function. That's the key component of the chain rule, is that you have to multiply by the inner function's derivative. Sorry, I didn't say derivative a minute ago. By the derivative of the inner function, which in this case is negative 3. So if I rewrite this, this is positive 3 times 2 minus 3x to the power of negative 2. Now, if this were my final answer, I would not want to keep that negative 2 power written in the problem. But because this is not my final answer, I really want to keep going and take a derivative again. It's more useful to me to keep that with a negative power. So I'll use, again, the outer function here is 3 times something to the power of negative 2. So I'm going to go ahead and use the power rule here, and I'll get negative 6 times 2 minus 3x to the power of negative 3. Notice that that base here stayed the same. That's the inner function, and I have to multiply this by the derivative of the inner function, which is another negative 3. So the final answer here, on the numerator, I would get a positive 18, and when I move the negative power down to the denominator, I'd have 2 minus 3x all raised to the third power. Now, number 7 is really an interesting problem, because on number 7, we're going to have to use the chain rule more than once, which you might not initially be able to see that looking at this. I'm also going to rewrite this power right here in a slightly different location to help us understand what's happening a little bit. It is important when we're looking with trig functions that we understand that a power written here is the power of the entire trig function. Versus if I had a power here, that would be a power of the argument only. So we do need to make sure we understand that. Now, I find this one helpful to rewrite like this. Negative 2 times the quantity of secant of 4x cubed raised to the power of 2. And keep in mind, this parentheses 4x cubed does not mean multiplication. This is the argument. This is the angle that we would be taking a secant of. This is an inner function. So this 4x cubed is an inner function. However, secant of 4x cubed is also an inner function. We have two different inner functions. We have secant, and we have inside of secant 4x cubed, which means we have to use the chain rule more than once. So I'm going to start by recognizing what the outer function is. The outer function is negative 2 times something squared. And so as I do the derivative, I want to start with the rule for the outer function, which in this case is power rule. So this would be negative 4 times something to the power of 1. Well, remember that you have to evaluate this derivative at the original inner function. And so at this point, the inner function, I have the entire inside here of secant of 4x cubed. Now I have to multiply this by the derivative of the next most inner function. So basically you're kind of moving from the outside in. So the derivative of secant, so the next inner function is secant. So I already did the most outer function, now I've moved into the inside, but I'm still kind of going from the outside in. So the derivative of secant is secant of the argument times the tangent of the argument. Well, this argument here must be the inner function of secant. It must be the same argument. So this would be of 4x cubed for that entire rule. And then there is another inner function. I've moved all the way now inside to that argument to the angle, and I have to multiply by the derivative of that inner function, which is 12x squared. I'm done with the calculus.